In this video, I'm going to introduce the idea of virtual memory. So up until now, we've been talking about the idea of main memory. When we talked about main memory, our basic goal was to say, okay, I have a bunch of processes running. I'm going to bring these processes into my main memory area, right? And maybe I can have a little bit of swapping, move them somewhere else to a packing store. But overall, the idea was I'm going to move kind of the entire process at a time, right? I'm going to basically assume that if a process needs stuff, well, it's going to be available, right? All of that process kind of is loading at the same time. So this is where we kind of stand. And we want to actually build an extension on it. We want to extend this a little bit. So the first thought here, right, and this is kind of a, this is a point people made, but maybe it's not so relevant these days, is one issue, right, with the idea of, I'm just going to bring in entire processes every time they run, is that we're kind of limited, right, to basically how large a process we can bring in. The amount of hardware I have, right, the amount of RAM I have, right, basically constrains, my programs to be, smaller than that, right? Because I'm saying that, normally I want to load the entire thing. Well, naturally, right, I can't have my memory be, my memory basically bounds the maximum amount of area, right, that I can have a process sit in. Now that's not really kind of a realistic thing anymore. We have so much RAM, right, that basically you're never going to have a program, right, that's larger than your 4 GB RAM or 16 GB RAM, whatever you may have. But in the past, right, in older systems, right, older architectures, you'd have the instance where maybe your RAM is only 32 KB, right, in which case all of a sudden you do have to worry about maybe there's a program that's larger than 32 KB and you can't load it, et cetera, et cetera. So that's kind of one issue, right, with kind of the notion of the main memory stuff we talked about in terms of bringing in processes and in whole pieces. So this is kind of an issue, and maybe, right, we can think about this a little bit and come up with a solution. So another thought, right, is basically this: when a program is running, I don't always need all of the program codes associated with it. So I may have my 32 KB executable, right, or let's say I have a 64 KB executable, right, and I have only 32 KB of RAM, right. At a glance, right, I can't fit that executable into that RAM, so I have no hope of ever loading it. But the thing is, in that executable, there's going to be a whole lot of different functionality that program provides, but yet when the user runs the program, they're not going to actually use all that functionality, right? They only may use these functions or these functions, right? They may not use all that 64 KB of program code. They may only use some kind of subset of it, right? Some fragment of it. So that's an observation, right? That's something we kind of make a note to ourselves. A second note to ourselves, right, is in addition basically to the footprint, right, from the executable itself, programs typically do some memory allocation requests. And so it might say something like, oh, can you give me 128 KB of RAM, right? Imagine you're doing something like a malloc. Now the issue with this, right, is again the same thing before, in that if I don't have enough physical memory, I can't grant that request, right? I have to have some sort of error code, right? I just have no hope of doing it, right, if I request more memory than I have physical space available. So that's kind of an issue. But then we can maybe also think that when I make a request like that, right, 128 KB, probably I'm not going to use all of it up front, right? Maybe I use a part of it here, part of it there. I don't actually need all of it up front. And so I have that. Maybe I can have some sort of an improvement because I don't actually need to allocate that 128 KB all in one shot, right? So this is kind of another observation here. So here's our goal, right? Or here's I guess our benefit, right? So if we care about these things, right? If we care about program not using memory that it requests, if we care about program not using all of its program code, the idea is we can hope to load basically some subset of it. So instead of having to bring an entire process into memory, right, grant all of its memory allocations in one go, what we can instead say is we're only going to do basically what the program needs, right? We're going to do some subset of it. That means basically that our processes will have kind of a smaller profile, right? They won't use so much memory anymore. They'll use a lot less memory. And then, right, I can basically have I'll be able to run multiple programs at once, is what you have at the end of the day, right? So we try to increase the amount of multi-threading, right, that is going on right now, right? Because we can basically have more programs in memory, because these programs, right, are still having to grant their entire request, right? We're only loading up the part of them that's actually needed right now. And so since my memory is finite, basically I can fit more things into that memory. That means I can have more programs running at the same time. That means I can have more things running in parallel, right, and get higher CPU utilization. So if I do this right, I'll get basically better performance in my system. So we're going to now introduce the idea basically of virtual memory. So virtual memory is basically going to say we're decoupling basically our pages from our frames. Before we said that there was basically this mapping for basically I have my main memory, right, which has a bunch of frames in it, right? I have my process which has a bunch of pages. There's a one-to-one mapping, and kind of those things always really lined up, right? It was intended that whenever you had a page, it lined up with some frame. The level of indirection in that kind of original discussion, right, about main memory was basically to say that this page can end up with some other frame. But somehow, right, every single page that was out there had to map to some frame. Now what we're saying is that's no longer the case. Pages are just kind of these virtual entities, and these virtual entities, right, may or may not be on the hard drive, right? Maybe they could be on the hard drive, right? They could be on your main memory, right? I'm basically having no guarantees about where exactly it's being stored. And so this is kind of an extension of what we saw before, right? We're just dropping the guarantee that all pages are in memory. We're saying that they could be anywhere. So let's take a look at the diagram on the right-hand side. So the diagram on the right-hand side has basically our process, right? Our process is running, right? So I have some process, P0, whatever. P0, right, is using this memory over here, right? So this is, virtual memory. And it has some pages, right? It has pages 0 up until I don't know how high. And there, right, there's kind of this virtual view, right? From the inside, the process sees, memory starting at 0, right? And it kind of just goes up forever, right? It can have basically an infinite amount of memory. And it has all that stuff to itself. And that's what we would have even had in the previous model as well. Our difference will be here in a second. So this is what the process sees, right? And the process, right, if it wants, it can basically utilize any of this space here, right? So if it wants to, grab a page, page, I don't know, 2000, whatever, it can go and grab that, right? Basically, I don't have any issue with sparseness. The process can just do whatever it wants. It lives all by itself. Now, in this new model, what we're going to say is the following, is that our pages, right, they'll basically be kind of recorded in something called a memory map, which is basically just going to be a page table. It's going to be a page table with a little bit more data associated with it. And then that page table is basically going to keep track of, is a particular page in physical memory, or is it on a hard drive? So I could have something like this. So in this case, I can look and I can say, hey, my program has these different pages. And for example, this first page over here, right, this is maybe we call this page 2, right? Page 2, is actually in physical memory. That's great, right? It's there right away. But then page 10 is not in physical memory. It's actually over in the hard drive. So in that case, right, basically, if I want to, access whatever is, at page 10, that means I have to maybe do some loading from the hard drive. Now, but from the point of view of the program, though, the program doesn't see any of that, right? So the program basically has this kind of wall here, and it just sees pages, right? It knows those pages available. Whether those are in main memory or in the hard drive, it doesn't know, right? The point is that in a virtual memory scheme, the program just doesn't care, right? We make no guarantee about the page where it actually resides. We'll just make sure that it's available when it's actually needed. So this will kind of address our issues as we had before, because basically what happens is that the most kind of active parts of your program are going to be running, and the rest of your program, right, is basically going to be sitting in your hard drive somewhere. And traditionally, right, your hard drive is going to be, in pretty much every case, right, your hard drive is going to be absolutely huge, right? It's going to be much larger than your physical memory, and so you're basically going to have the ability to store anything you want there. And of course, we can kind of do some of the optimization we talked about earlier, where we basically say that different kind of pages, right, can basically reference the same frame, right, if they're kind of storing the same piece of data as well.